Okay, molar mass. So we often need to know, as chemists, how many atoms are in this sample that we have. And the reason that we need to know that is because chemical processes happen between particles. When you make a water molecule, it's 2 hydrogen atoms and 1 oxygen atom. It's exact numbers of particles. And so when we look at larger quantities, we're still referring to numbers of particles. So if you were, wanting to know how many pencils were in a box, you could just count them, right? If you wanted to know how many, now I live in Reedley where there's a lot of fruit. Right now it's oranges. So you've got a semi-truck full of oranges. You want to know how many oranges are in the truck. You're going to take them all out and count them? No. You're going to weigh the truck. Find the weight of the oranges. Then if you know the average mass of an orange, you can estimate the number of oranges that are in the truck, right? Nobody's going to count that. We have large numbers of objects in everyday life, and we don't count them as individuals. We have counting units. A dozen is a counting unit. A dozen objects is just 12 objects, right? You can have a dozen donuts, you can have a dozen pencils, you could have a dozen people, a dozen countries, a dozen galaxies, a dozen anything. It's just 12 of those things, right? Everybody's cool with that. There's another unit you might not be as familiar with, which is a gross. Don't know where that came from, but 1 gross. A gross is 144 objects. It's a dozen. 12 times 12 is 144. Another counting number or unit is a ream. So you go to the office supply store and you buy 1 ream of paper. That's not a particular height of a stack or how much it weighs. It's how many pieces of paper. It's 500 pieces of paper. We have these units because they are convenient for the quantities of stuff we're dealing with. You don't want to buy pieces of paper by the dozen because generally you buy far more than 1 dozen pieces of paper. So ream is useful, 500 sheets of paper. But a ream would not be a useful thing for donuts or bagels, right? Because how often do you need 500 bagels? Not very often. Well, chemists have their own counting unit because even the ream is far too small when we talk about counting atoms. So the chemist's dozen is the mole, okay? M-O-L-E. It's abbreviated M-O-L. It's a short word. I don't know why it needs an abbreviation, but it has one, so there it is. A mole of anything is this crazy number of that thing. So 6.02214 times 10 to the 23rd units. That is a mind-bogglingly large number. That's a 6 with 23 zeros after it. It'll take you a while on the chalkboard to write it out even. So when we talk about a mole is the amount of material containing that many particles. You could have a mole referring to atoms, to ions, to molecules, any particle. This number, and here it is with 6 significant figures. Usually we just use 6.022 times 10 to the 23rd, and that is a number you should memorize. 6.022 times 10 to the 23rd. That is called Avogadro's number. It's named after the scientist whose work led to the discovery of that number. So this is a useful quantity for expressing atoms or molecules in reasonable quantities. So a mole of copper atoms is about 22 copper pennies. So 22 pennies, you can hold those in your hand, right? It's small enough that you can just handle it and deal with it, but large enough that you can see it, right? So it's convenient. A tablespoon of water is approximately 6.022 times 10 to the 23rd water molecules. So this gives us a useful quantity of matter, Avogadro's number. Any questions? Where did that number come from? Well, it's related to the definition of the atomic mass unit. So the value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. Now, we referred to carbon-12 earlier, right? An atomic mass unit is 1/12 the mass of a carbon-12 atom. The mole is the number of atoms in 12 grams of carbon-12. This gives us a very nice relationship between grams, numbers of atoms, and also atomic mass units. I'm getting ahead of myself. So 12 grams of carbon is 1 mole of carbon atoms, which is Avogadro's number of carbon atoms. We can convert between moles and numbers of atoms in the same way that we use dozens. So we can convert between eggs and dozens of eggs, right? You go to Costco and you can buy 5 dozen eggs. How many eggs is that? 60. How did you figure that out?
12 times 5.
12 times 5. 5 dozen means 5 groups of 12, right? There are 12 eggs in a dozen. So we do the same sort of conversion using moles. 1 mole, 1 chemist dozen, equals 6.02 times 10 to the 23rd atoms. So mole is like dozen, and that crazy number is like 12. So we can make conversion factors from this relationship, moles on top, atoms on the bottom, or we can turn it upside down. Sometimes students get the number with the wrong thing. They'll tell me that it's Avogadro's number of moles is 1 atom. Well, convert that into dozens and 12 and ask yourself, does that make sense? 12 dozen is 1 egg? Wait a minute, that's not right. Okay, so switch the numbers back. So let's do an example. Pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? So as with many of our word problems, this is a dimensional analysis problem. So we have to identify what are we given, where are we starting, and what are we trying to figure out? Well, there's only one number in this problem, so that's probably where we're starting. They're telling us we have this many silver atoms, and the question is, how many moles? So our path here is pretty short. It's just atoms to moles. The relationship between atoms and moles is Avogadro's number. So 2.80 times 10 to the 22 atoms. And then our fraction here, because we have 1 arrow, we have 1 fraction. The numerators here, atoms to blank. It's what we wrote up here, atoms to moles. So atoms are here, moles go here. And atoms go on the bottom. You get the unit in first, and then you put in the numbers. So I graded your worksheet 1A over the weekend. I actually went through and looked at all of the answers. Some of you did really well. Some of you are a little confused about the process of dimensional analysis. Now is the time to ask me questions and get that straightened out this part of the semester, because it's not going to go away. We need to be able to do stuff like this with units. So we put the units in first, and then we stick the numbers in. So we've got moles, which are like dozens, and atoms that are like eggs. So it's 1 mole, 1 dozen. 1 dozen is 12 eggs, so 1 mole is 6.022 times 10 to the 23rd atoms. So we've got it written down. Now we need to make sure that we communicate correctly with our calculators. So if you have your calculator, pull it out and actually do this with me. Your calculator should be a scientific calculator, and it should have either an EE or an EXP button. I think there's some Casios that have a times 10 to the X button. You got to be careful with those. So the EE or EXP stands for times 10 to the. So to put this number in, I'm going to put in 2.80, and then I'm going to press EE. And as I press that, I'm thinking times 10 to the. You're not going to press the multiplication sign. You're not going to type in 10 and then EE. You're just going to do the EE button. Okay? So I'm going to I got to turn it on first. 2.8 EE, and then I put in the exponent, 22. I press the EE button. My calculator is only showing me E. That's okay. And then I'm going to multiply by 1. You can skip that if you want to. And then I'm going to divide by 6.022 EE 23 and press equals. And so I can look at these and predict that this should have 3 sig figs, because this one has 3 sig figs and that has 4. So my calculator is showing me 4.64. There's my third sig fig. I'm just going to write down 2 extras. And then times 10 to the minus 2. Because it's set to display in scientific notation. Calculator might be showing you it like this. Different ways of expressing the same number. If you're getting a very large number here, that means that when you're dividing by this number, you're actually only dividing by 6.022, and then you're multiplying the whole thing by 10 to the 23rd. And that gets you a wildly wrong answer. So if you're having trouble with that, communicating with your calculator, please talk to me during lab, and we'll get that straightened out. To round this, I would keep that 4. So I write it as 6.4. The 4 is going to round up to 5 because the next digit is a 9. Times 10 to the minus 2 moles, or 0.0465. Either of those are acceptable. Any questions? Yes? That's a good question. Do you need to specify atoms of silver, moles of silver? In a question like this, you don't have to. Later in the semester, we will have to specify because we'll be starting with silver and we'll be ending up with silver oxide. So if you've got different kinds of atoms, then you have to specify. Good question. Any other questions? So we talked about counting oranges by weighing them. And we count atoms by weighing them as well, because you can't count them individually. We have no choice. But we need one other conversion factor. The mass of 1 mole of atoms. So the mass of 1 mole of atoms is the molar mass. So the atomic mass is the mass of an atom. The molar mass is the mass of a mole. And this is where how these units were defined becomes convenient. And this was intentional. This wasn't a happy coincidence. The element's molar mass in grams per mole is the same as the element's atomic mass in atomic mass units. So if we have 26.98 grams of aluminum, that's equal to 1 mole of aluminum atoms. If we look on the periodic table for aluminum, we see that the atomic mass is 26.98 atomic mass units. So that number does double duty. Atomic mass units tells us the mass of 1 atom, the average mass of 1 atom. If we use the unit gram, it tells us the mass of a chemist's dozen of atoms. So those numbers on the periodic table, under carbon, you'll see 12.01, because that's the average mass of carbon. That's Avogadro's number of carbon atoms. Helium, 4.003 grams, Avogadro's number of helium atoms. So we've got the same number of atoms of each of these elements, but the masses are different because the atoms are different sizes. So this would be like a truck full of grapefruit, and here's a truck full of oranges, and this would be a truck full of, I guess, kumquats, right? Those little weird little guys, right? If you had the same number of each fruit, they would have different overall masses because each piece of fruit is a different mass. Does that make sense? So the mole is talking about a number of things, okay? Converting between mass and mole. So that molar mass of the element is the conversion factor between the mass in grams and the amount in moles. So we look at carbon, we find out in the periodic table 12.01 grams is equal to 1 mole. We can make that into very nice conversion factors so that we can use the mass of our carbon sample and figure out how many moles of atoms we need, or we have. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So we have 35.8 grams. Now, we do need to know that this is copper, because if they didn't specify the element, we couldn't do this problem. So we know it's copper, and we're trying to find out how many moles of it. So we say moles of copper. Well, how much does 1 mole of copper weigh? Got to look at the periodic table. 63, I'm going to round that to 55. 63.55. So Avogadro's number of carbon atoms weighs 63.5 grams. 1 carbon atom weighs 63.55 atomic mass units. So this is our conversion factor. So we'll do this. We can do this in one step. We have 35.8 grams of copper. We have 1 fraction here. We're going to have moles on top and grams on the bottom because we want the grams to cancel out. 1 mole is this many grams. 1 mole for 63.55 grams. So 35.8 divided by 63.55. This also should have 3 significant figures. I'm going to write down 2 extras. So it's moles. 0.563 moles of copper. Any questions? Dimensional analysis, once you get the hang of it, makes these problems a lot easier. Because you don't have to remember, do I multiply by the molar mass or do I divide by the molar mass? You put the units in, the units tell you you're going to divide. You don't have to remember. You put the units in and then the numbers and everything's fine. So now we have everything we need so that we could count atoms by weighing them. So you would need the mass of the sample. You'd convert the mass in grams to the amount in moles, like we just did using the element's molar mass. And then from the number of moles, we can figure out how many atoms there are using Avogadro's number. Now, are we going to get the exact number of atoms in that sample? No. Do we need to know the exact number? No, we don't. We want a good approximation, and that's what we're going to get. So grams of element to moles of element to number of atoms. The conversion factors are the molar mass and Avogadro's number. So how many carbon atoms are there in a 1.3 carat diamond? And some information we need. Diamonds are a form of pure carbon, and 1 carat is equal to 0.20 grams. So the number that we're given in this problem is 1.3 carats of diamond, right? So 1.3 There's an abbreviation for that, but I don't remember what it is. And what are they asking us for?
How many carbon
Atoms,
atoms?
right? So we're looking for atoms of carbon. So we've got this many carats of carbon, and we want to know atoms. Oh, that's a weird unit, isn't it? But here we're given the relationship between carats and grams. So we could convert carats of carbon to grams of carbon, right? That was handed to us. Grams of carbon to atoms, what unit are we going to use in the middle? Moles. So we'll go from grams of carbon to moles of carbon to atoms of carbon. This conversion is using Avogadro's number. Grams to moles is using the molar mass from the periodic table. So now we can write it out, putting all the units in. So we've got 1.3 carats, and this one has 3 arrows, so we're going to have 3 fractions. So carats to grams to moles to atoms. Carats to grams to moles to atoms. Once you get this path figured out, once you figure out what units am I going through, then it's just a matter of following a pattern. So I put those units in the numerator, and then I need carats to cancel out, so I'm going to put that in the denominator. So carat goes down here, so they cancel. And gram goes down here. And moles go down there. Put all the units in. The units then tell me what to do with the numbers. Here, carats and grams. I look at the relationship here. 1 carat. So I write 1 in front of the unit carat, and that's equal to 0.20 grams. What's very important about each of these fractions is what's in the numerator has to be equal to what's in the denominator. 1 carat equals 0.2 grams. If they're not the same, I can't use it because it's going to change everything. Moles and grams. So this is carbon. This relationship between moles and grams comes from the periodic table. It's always 1 mole is how many grams. So you look under the symbol for carbon and you see 12.01. Atoms and moles, it's like dozens and eggs. A mole is like a dozen, so it's 1 dozen is 12 eggs. A mole is that crazy number, 6.02 times 10 to the 23rd. So then we do the math, just go left to right, multiply by the top, divide by the bottom, skip the ones if you like. So 1.3 times 0.2, divide by 1, times 1, divide by 12.01, times 6.022 EE23 equals. Based on the numbers that I'm given starting out here, I should have 2 significant figures. So I'm going to make sure that I write down the 2 significant figures and 2 extras. So I'm going to write down the next 2 digits, and you don't have to worry about rounding those. That's why you use 2 of them. So that's going to round to 1.3 times 10 to the 22 atoms. Any questions? It's always good to look at your answer and ask yourself if that's reasonable. Is it reasonable to have this ginormous number of atoms in this diamond? Yeah, because atoms are crazy small. Anytime you have enough substance to see, you're going to have a huge number of atoms. Question? How did I get the significant figures? So the starting number here, the mass was 1.3 carats. So that has 2 significant figures. And this relationship is given to me as 2 significant figures. So I've got 2 here and 2 there. This has 4 and that has 4. Multiplying and dividing, I use the smallest, which is 2. Good question. Any other questions? Let's do another one. Titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeter. We haven't talked about a problem like this, have we? We're going to talk about this one now. There could be a problem that surprises you on the exam. In fact, that's my intention, to put at least one, if not 2 or 3 problems that pull concepts that we talked about together in a way that you haven't seen before. That tests critical thinking. So don't complain when that happens, because I just told you it's going to happen. So what do we do? Well, we read the problem. A good first step is write down the numbers with their units. So let's write that down. We've got 2.86 times 10 to the 23rd atoms of what? Titanium, right? So titanium is Ti. And then we have a density, 4.50. Now that's written with a slash, so that gram per cubic centimeter is on the same line. It's done that way because it's so much easier to type into the computer. To do a vertical fraction, I have to break out the equation editor, and it's annoying. But when you're writing out by hand, it's just as easy to write a vertical fraction as a horizontal fraction. So always write those as vertical fractions like this. Because when you draw a horizontal line for the fraction here, that tells you very clearly I have a numerator and a denominator. What I see when people do it like this is you overlook the fact that that's a fraction and you end up with some very odd answers. So write it as a vertical fraction. So then the question is, what's the edge length of a cube? We've got a number of atoms and we have a density. Well, let's maybe draw a picture of the cube here. From geometry, what do we know about the relationship between the volume of a cube and the length of its sides? Yeah, a cube is going to have all the same sides. I mean, the sides are going to be all the same length, right? And so the volume is going to be the length of the side cubed. Height, length times width times height, and they're all the same, so call them L. So there's a relationship between the volume of this cube and the length of the side. This density has a mass unit and a volume unit. So I'm trying to get length. What might be a unit for length? Centimeters? So if I knew the volume, I could find the length, right? The volume, a convenient unit might be cubic centimeters. This density relates mass and volume. So what I'm doing here is I'm working backwards. I'm working from the end back. Sometimes it's easier to work from the front and go forward. Sometimes you have to work from both ends and hope that you can meet in the middle somewhere. So I have a relationship between grams and cubic centimeters. So if I had grams, I could get to the volume of it in cubic centimeters. But I don't know the mass. But we just learned how to figure out the relationship between numbers of atoms and the mass. What was the unit that we used in the middle?
Molar mass.
Yeah, we used the molar mass to calculate the moles, right? So, remember the TV show Malcolm in the Middle?
Yeah.
Yeah. So Malcolm in the middle, moles in the middle. We'll often find that mole is a unit that shows up in the middle of our calculation. So if you're missing a piece, try moles. It might be the right one. So this is our path. Atoms to moles to grams to cubic centimeters to centimeters. Figuring that out is the hardest part. So let's start. 2.86 times 10 to the 23rd atoms. And I've got a conversion factor here. So that's going to be moles on top, atoms on the bottom. And then another conversion factor with grams on top and moles on the bottom. And then another one where I have cubic centimeters on top and grams on the bottom. How do I get from cubic centimeters to centimeters? Is there a conversion factor for that? No, there isn't. There's an equation, right? So this is an example of a problem where we're doing unit analysis, dimensional analysis, but we also have to use an equation. So this is the equation. So I'm going to stop my dimensional analysis here. I'm going to get cubic centimeters, and then I'm going to make use of the equation. So I can stick the numbers in. Here's my density, 4.50 grams. So 4.50 grams there. There isn't a number in front of cubic centimeters. If that bothers you, it would be a 1. Grams and moles. Periodic table, right? Titanium. That's not one that I remember. Where'd you go? 47. 47.87. So 47.87 grams is the mass of 1 mole of titanium atoms. And then we've got the mole and the atoms again, like the dozens and the eggs. So 1 dozen is 12 eggs. 1 mole is the crazy number. So then I do the math. Am I expecting a really huge number or a really, really small number? No, probably kind of like just a regular sort of number, right? Because I've got this giant number, but I'm dividing by a giant number, and these other numbers are kind of reasonable. 2.86 EE23 divided by 6.022 EE23 times 47.87 divided by 4.5. This one has 3 sig figs, this one has 4, this one has 4, this one has 3. The smallest number of sig figs is 3. So I'm getting 5.05. I'm going to underline the third digit. That's my last significant figure. I'm going to write down 2 more digits, and then the unit that's left here is cubic centimeters. This is not my final answer. I do not want to round this. I want to keep those 2 extra digits until I get to the end. So any questions so far? So there's my equation, right? So volume equals the length of a side cubed. Well, I want to know what L is. So I need to rearrange this equation and solve for L. So if I take the cube root of both sides, the cube root of V and the cube root of L cubed, the cube root of L cubed is L. There is algebra in this class. Sorry. I'll help you with it, though. So L equals the cube root of the volume, and this is the volume I just calculated. So the cube root of 5.0521 cubic centimeters. So your calculator should allow you to calculate that. On mine, I have a whatever root you want button. And so that's 36X Pro calculator. I'm going to press 3, and then that, let me see. 3 box root 5.0521 equals. Yeah, I think that worked. And my calculator is showing me 1.7158. You take the cube root of centimeters cubed, you're going to get just centimeters. You can check that to make sure that you were okay with your calculator by cubing your result or multiplying by it a total of 3 times, and yeah, I get the same number back. You have to learn how your calculator works. That's why if you have a programmable calculator, those are great, and you probably had to get it for a math class. You're not going to be able to use it on the final exam. So I would highly encourage you to get a TI-36X Pro. It'll take you through Chem 1B as well. And get it now, become familiar with it so that you're not surprised by using a different calculator on the final. So then I would round this 1.72 centimeters is the edge length of the cube. Any questions? You should be able to do a problem like this in a reasonable amount of time. Oh, thank goodness.